Okay, welcome back. So I watched the last video. Wasn't too bad. Things were a little bit crooked. Hopefully I got the camera straightened out and it's a little bit better, but it wasn't as bad as I thought it could be, but there's always room for improvement. Anyways, last time we looked at two problems. We looked at vertex cover and we looked at independent set. And the graph that we inspected, in the context of these problems looks something like this. In fact, I believe it was exactly like this. The goal of this portion of the lecture is to try to relate these problems to each other and get an ordering of these problems. When I say an ordering, I mean I want to reduce in polynomial time one of these problems to the other one. So before we see how to do that, let's take a look at some things we observed last time. So I have a C1 here and I have a C star. So C for vertex cover, and this was just a vertex cover we found in the graph before. And C star, whenever I use a star, it's going to mean optimal in some way. So this is an optimal vertex cover, meaning it's the smallest possible vertex cover in this graph. On the flip side, when we looked at independent sets, we noticed that the empty set was an independent set. And that's going to be true in any graph. It's certainly true in this graph. And then I have this I star. So that's going to be the optimal or n optimal. In fact, it's a unique optimal in this particular graph, but in general, there could be many optimals. So I should say it's n optimal independent set. And we observed last time that this equals 1, 3, 4, 6. Remember, with independent sets, we want the largest set possible. With vertex cover, we want the smallest set possible to be a vertex cover. With independent set, we want the largest set possible. I want you to take a moment and we're going to try to relate these problems to each other. And can you make any observations about this? Well, C1, that's a vertex cover, and I1, this is an independent set. This is the optimal vertex cover in this particular graph, and this is the optimal independent set in this particular graph. What observations can we make? Well, you look at that. Geez, okay. Well, first of all, maybe the first thing we're going to notice is they never share vertices. So you look here. There's no vertice that appears here that appears in this particular independent set. Okay, is that the only observation I can make? Does that even hold? Well, I look at the optimal vertex cover and I see, okay, well there's 2 and 5 here. Did 2 and 5 appear in the optimal independent set? Not quite. In fact, they don't at all. So that's a pretty solid observation. It seems like there's some kind of relationship there. But let's check this out too. If I take the union of these two things, I get back exactly V. How am I going to relate these two things? Well, based off this, maybe we can guess, what if this holds? I'll put a question mark here for now because we haven't proven it yet. What if it holds that if C is a vertex cover in G, then V minus C, I think V minus C is just the difference between the original set of vertices and the vertex cover C, is an independent set in G. That would be a pretty powerful result. And in fact, we can maybe even make this a little bit more powerful. So this is saying if C is a vertex cover in G, then V minus C is an independent set in G. I'm going to change this just a little bit here and say C is a vertex cover in G if and only if V minus C is an independent set in G. That's an even more powerful statement. And how would we use that? Well, remember, we're trying to relate these two problems to each other. If this is true, and we haven't proven that it's true or not, but if this is true, it's a pretty powerful relation between these two problems. And when we relate problems, what I'm really talking about here is I want to reduce one problem to another. Like I said, last time we saw that vertex cover is in NP. I don't know if it's in P, If it wasn't P, I'll tell you this right now. If it wasn't P, P would equal NP. Big news, or at least big news in the computer science community. I don't think we discussed it explicitly last time, but you should be able to convince yourself that the independent set problem is also in NP. And it's the same thing. May be in P, may not. If it is, then P equals NP. And we formally define these problems as follows. I call them vertex cover problem. Remember, problems are languages, languages are problems, etc., etc. And we defined it something like this. GK there is a vertex cover in G of size K or more, or less. Remember, we're always trying to get the smallest possible vertex cover. I'm going to define another language. I'm going to call this independent set, IS for independent set. And it's going to take in a G and a K. And I'm going to say this is the language where there is an independent set. So again, I'm kind of overloading this IS and VC. I think you can figure out what I mean here. But there is an independent set in G of size K or more. So it is actually or more on this one. Because remember, we're interested in finding the largest independent set when we're looking for independent sets. So these are my two problems. I want to relate these two problems to each other somehow. How am I going to do that? Well, we have to use reductions in some way. And for a moment, let's just assume this theorem does hold. So if this theorem does hold, can I come up with a reduction? And I'm going to be a little bit more explicit here. Which way are we reducing? We're reducing vertex cover to independent set to vertex cover. Let's start out with reducing independent set to vertex cover. So we'd write something like this. Independent set reduces to vertex cover. This is what we want to show. And if we show this, this means vertex cover is at least as hard to solve as independent set. In other words, if I can come up with a polynomial time solution for vertex cover, and I know a reduction from independent set to vertex cover, then I get a polynomial time solution for the independent set problem for free. Okay, how would we show this? Well, let's for a moment just assume that this theorem is true. If we assume that theorem is true, can we come up with a reduction from independent set to vertex cover? Well, remember, how do we come up with a reduction? We assume we have a black box that solves the vertex cover problem for free. So I can ask it questions. I can give it a G and ask, is there a vertex cover of size K or less in G? And it's going to return to me yes or no. And it's going to work, guaranteed, some kind of magical black box function. And we're going to assume it runs in constant time. Given access to that black box, I need to be able to solve the independent set problem in polynomial time. So I want you to take, pause the video, just take a moment to think about this. It's not that tough. Look at this theorem. It boils down to something pretty simple. Pause the video, try to tackle that reduction on your own first, and then unpause and we can continue. Okay, welcome back. So think of it like this. Given GK, I want to know, is there an independent set in G of size K? Well, I'm going to ask my vertex cover black box solution, does there exist a vertex cover of size something And just bear with me for a moment. Let's try v minus k. The magnitude of v minus k. Does there exist a vertex cover of size v minus k in G? So I'm basically asking it, I pass it in G, and I pass it in the number v minus k. Well, I'm not sure if that works or not yet, but assuming this theorem is true, it should be relatively clear that that does work. Because remember, I'm wondering, does there exist an independent set of size k? Well, if there exists an independent set of size k from this theorem, there has to also exist a vertex cover of size v minus k. You do the math, so imagine v minus c, the magnitude of v minus the magnitude of c. Well, if I let that equal k, remember this is my independent set. So what's the magnitude of c? Do some simple algebra here. Magnitude of v minus k equals the magnitude of c. So the magnitude of my vertex cover is going to be the magnitude of v minus k. And remember, this is if and only if. That's a very important point. Why is that an important point? Well, that's going to make sure that if there is an independent set, this vertex cover black box is going to give me a yes answer. So I know there is an independent set. And if there isn't an independent set of size k, this is guaranteed to give me a no answer. Okay, well that's actually pretty easy. I mean, I just have to ask the black box one question. I really don't have to do any manipulations on G, and I just have to do a quick calculation for this. That's certainly polynomial time. So if this is true, this is a polynomial time reduction. Okay, well that makes sense. That means I can reduce independent set to vertex cover if this theorem is true. But is this theorem true? Well, that's what we're going to explore for the remainder of lecture. Let's think about it. Let's look at that theorem and try to prove it. How would I go about doing that? Well, let's first try to show that if there's a vertex cover of size k, or v minus k, whatever one you want to let it be, then there's going to be an independent set of size k or v minus k, again, the inverse of that. Okay, so we're going to try to show if there's a vertex cover in G of size k, then there's an independent set in G of size v minus k. Oh, you know what? For simplicity, let's just keep it this way. We're looking for an independent set of size k. So let's assume, it works either way, but let's assume there exists a C, a vertex cover C, of size magnitude of v minus k in G. Okay, assume that C exists. I'm going to try to prove that given that C exists, that there's an independent set of size k. Well, what's the independent set going to be? Well, look over here at this theorem. This seems like a good candidate to start, a good place to start. And based off our observations before from that graph, what if we just take the original set of vertices minus off the vertex cover? Is that an independent set? If it is, we've certainly proven this point. We still have to go back and prove it the other way as well. But let's consider that. Consider V minus C. Well, the first point I'm going to make is, and this would kind of be an aside here, running out of room. These whiteboards, they're so small, but you got to work with what you got. I'm just going to make a little side note. The magnitude of V minus C equals what? Equals K. So if V minus C does end up being an independent set, then I have proven this first point here. But I mean, how do you prove something's an independent set? Well, let's consider two vertices in this particular set. Moreover, consider V1 and V2 that are elements. Oh boy, I've backed myself into a corner. Got enough room. Hopefully you can read that. So V1 and V2 that are elements of V minus C. And some brackets around there. That's rough. Oh well. So remember, V1 and V2, they're elements of V minus C. Now here's the question I'm going to ask. Is the edge V1, V2 an element of E? What's E? E is the set of edges in G. Remember, what's the graph? It's just a set of vertices, a set of edges. We've been using V all over the place. E is just a set of edges. What's an edge? Well, it's a two-tuple of vertices. Your start node and your end node. So I'm trying to figure out this question. Is the edge V1, V2, and E? Remember, V1 and V2 are both elements of V minus C. And I want you to just ponder that for a moment. Well, what if V1, V2 was an element of E? Well, that implies that V1 is not an element of, and this is just by definition of V1 and V2 being in this set V minus C. So V1 is not an element of C, and V2 is not an element of C. Remember? Okay, so V1's not an element of C, and V2 is not an element of C. And, look at this, the edge, V1, V2, is in my graph. So think about this. My graph looks something like this. V1, V2, and there's an edge between them. I'm saying, consider the case of there is an edge between V1 and V2. The rest of my graph's going to look, arbitrarily complicated or simple, right? We're going to have a bunch of nonsense over here potentially, or maybe it's not nonsense at all. But remember C. C is a vertex cover. And what does a vertex cover do? It's a set of vertices that covers all the edges. So maybe this is an element of C, this is an element of C, maybe that one's an element of C. And it's covering some of these edges. But look, is there an edge in here that isn't covered by C? Yeah. What edge is that? Look right here. V1, V2 is not covered by C. Why? Well, I know V1's not an element of C, and I know V2's not an element of C, and I know this edge exists because I'm assuming it does. Well, what does that mean? Well, if that's true, therefore, C is not a vertex cover. But it is a vertex cover. So I have a contradiction. So what does that mean? That means V1, V2 cannot be an E. And let's look at the edge V1, V2, or the vertices V1 and V2. I said take any two vertices in the set, V minus C. So V1 and V2 are arbitrary vertices in V minus C. So therefore, V1, V2 is not an E. Remember, that's the conclusion, and that's true for any V1 or V2 in the set V minus C. Okay, well that's not an E. So what? What does that mean? Well, therefore, no two nodes or vertices in V minus C are directly connected. What do I mean by directly connected? There's no edge between them connecting, V1 directly to V2. So no two nodes in V minus C are directly connected. Okay. Well, if I have this set, it's a set of vertices, v minus c. No two nodes are exactly connected, or sorry, no two nodes are directly connected. What does that mean about that set of vertices? Well, what was the definition of an independent set? Independent set was a set of vertices with no direct connections, no edges between them. Well, that's what v minus c is. Therefore, v minus c is an independent set right on. Okay, so we're almost done. Why aren't we done? Well, all we did here was prove that if there's a vertex cover C, so C has size v minus k, then there exists an independent set of size k. So we showed that, okay, if there is a vertex cover of size v minus k, then there is an independent set of size k. But that's not all we need for the reduction. What else do we need? Well, we need it to be if and only if, so we need to show, okay, it goes the other way as well. If there's an independent set of size k, then there's a vertex cover, so we need to show, okay, independent set size k implies there's a vertex cover of size v minus k. We also need to show it that way. We showed that if there's a vertex cover of size v minus k, then there's an independent set. But instead of doing it this way, I'm just going to take the contrapositive and say, okay, if there doesn't exist. So if there doesn't exist, how do I want to write that? If there's no vertex cover of size, and I know I'm in the way, I'm trying my best. If they're, gotta make sure the grammar is correct. Putting on YouTube is there forever. So, I mean, I'm one of the worst spellers out there. I'm gonna make tons of grammar errors, tons of spelling errors on these things. Based on spelling, I certainly should not have a PhD, but that's not the way the world works, so too bad. If there's no vertex cover of size v minus k, this implies there's no independent set of size k. How are we going to show that? Let's think that through. So that's what we need to show. If we can show this, then we've shown the reduction. So the one thing I need to start doing is keeping track of time. Because the one thing I did not expect about YouTube was it takes forever to upload these things. So I'm going to give myself the option here of ending short, but we'll see if I need to cut it here and do another one or just continue on. So here's the pretend it's over.